This is the end of chapter 5, which is chemical reactions. And the last topic was we'll not take the heat or something. We'll take most probably the percentage yield. We talked about the heat. We talked about exothermic, endothermic. But the main thing is how to calculate the percentage yield. The PowerPoint, it looks like it's not have specifics. I found for you guys a very nice, let me just here show you here, very nice worksheets, which is those, by the way, those worksheets, they are dynamic, meaning you find them today, you might not find them in a couple of years, so you find even better ones through the years. So as I said, those are free, you don't have to pay for them. So let's look at this percentage calculation. First, we have to know what formula we have to use for this percentage yield. There is a formula. And as I said, you have to put this formula aside whenever there is a question in the quiz or the exam, quiz number 3, exam number 3, then you will be ready to answer this. So what's the percentage yield? They call it like this, yield. Or sometimes they put the yield and they put this one here. Whatever you prefer. Some textbook will put the percentage before. Some will put the yield and the percentage. Whatever. The main thing is a percentage yield. So this will be, the formula says actual yield divided by the theoretical yield and the whole thing multiplied by 100%. So actual yield actually is always given to you. It is. That's always given. Always given. It has to be given to you because this is based on experiment. Based on experiment. You will not do the experiment inside the worksheet, correct? Based on experimental lab. Okay. However, the theoretical part of the yield is coming out of calculation. So the theoretical yield based on limiting reactant calculations. Okay, guys? So actual is always given to us because we'll not do the actual experiment inside the worksheet, correct? That's already, there is an experiment in lab have done, and they give you the value of this, what they got, what they obtained from the experiment. The theoretical one you have not done any experiment, not experiment yet, no experiment done yet, no experiment done yet. So no experiments done yet. So you base yourself, if I put this one, how many grams of this reactant will react with how many grams of this the other reactant to give me how much of the yield, theoretical yield of the product I'm looking for. So that's, you have to determine which one is limiting reactant. Then from the limiting reactant, you'll base your calculation on the in order to get this theoretical yield. However, through the years, I've seen these ACS exams will not give you the limiting reactant direct. Will give you one limiting, one excess. Will tell you one is in excess, means that's, you don't have to calculate the limiting because you know which one is limiting, correct? If I give you, or the ACS exam, not me, but the ACS exam, always give you the limiting, the excess. So you can figure out that the other reactant will be what? Limiting, correct? So here it is, write it there. We'll say excess reactant, those type of questions of the ACS exams, reactant uh, is given. We'll tell you one of them is in excess. So that's the other the other reagent or the other reactant is limiting. The other reactant is limiting. So with this in mind, then we'll see what's the problems there. So you have everything. Everybody has this. Take your time. Take snapshot of it, your phone, whatever. So everybody has this. Okay. So okay, guys. So everybody has it, correct? Everybody has it. Okay. Thank you. So let me take it out. Main thing is actually divide by theoretically multiply by 100. Actual is given to you, correct? Theoretical, you have to calculate it to calculate this yield from limiting reactant. Actually, in ACS exam, the time is limited. If you calculate the limiting reactant, not like our online assignment, Chem active, Chem 101 active, you have time. But there in ACS exam, the time is really really very short to do all those calculations. They will give you one reactant in excess, so you have to figure out the second reactant is what will be limiting. So let's look at this example, guys, and we'll do it step by step, all of us here. So we have magnesium will react with nitric acid to give us magnesium nitrate plus hydrogen. They want to see how many grams of hydrogen is produced. This is our product. This is the second product too. This is a product, but we are interested in this hydrogen, correct? And this is a product too, but we are interested in this one here, in hydrogen, correct? And they will give us how much of the reactant we have to use. This is a reactant here, and it's telling us this has to be what? Limiting. Why? Because nitric acid, excess of nitric acid. So nitric acid is an excess reactant, correct? And this reactant here, magnesium reactant, is limiting, correct? So we know that's limiting reactant, so it's limiting. So therefore, we have to base our calculation based on this limiting reactant, correct? With the magnesium. It's given us magnesium 40 grams. We have to do decimal here, please. They should have the decimal, but some worksheets, they don't care about significant figures. But anyway, we do care. So now, first of all, they ask what type of reaction is this magnesium with nitric acid? This magnesium acid here, magnesium plus nitric acid give us magnesium nitrate plus hydrogen. The type of reaction is given to you, is already written here, is what? Single what? Displacement or replacement, correct? So this is type of reaction, single displacement or replacement. Now let's do the calculation. You start always whatever is given to you. The 40 grams here, we'll put a decimal here as a 2 sig fix, correct? And then the next step is, I have gram of magnesium, I have to get rid of the gram. I divide by the atomic mass. So divide by atomic mass of magnesium. Then I come here and look at the ratio from the chemical equation. Here it is, mole ratio from chemical equation, correct? And then the last one here, I have to multiply by the atomic mass, divide here, multiply by atomic mass of hydrogen, by atomic mass of hydrogen. This is the product. So let me repeat myself. 4 steps. They give you the grams of the reactants. The first thing is you put those grams of the reactants as they are, divide them by the atomic mass, or if you have a molecule, by the molar mass. Atomic mass if you have element like magnesium by itself, or molar mass of this limiting reactant. Then you go, the third step is to look at the chemical equation. What is the mole ratio of the product you are looking for? 1 to the reactant, limiting reactant 1 to 1 magnesium. So, and then you multiply it. The fourth step is multiplying by the atomic mass or molar mass of the product in question, or you want to obtain it. So, correct? And it came out to be this. This is called theoretical what? Theoretical yield. Based on the limiting reactant is magnesium. Sorry about this. Okay, the 3.3 grams, 2 sig fix, because I put the decimal here. They should have put the decimal here. So 40 with the decimal is 2 sig fix. Okay, guys. So maybe there is I can't see this sig fix, but I put a 40 like this. So 3.3 gram of hydrogen. This is the theoretical. Everybody's following? Everybody's following? Take a snapshot of this. Take a snapshot of this and we can proceed. So we got the theoretical one. And now the actual yield will be given to us always, correct? Based on the actual experiment. This calculation before you do the experiment, before you start the experiment, you know how much you can expect to get. And that's what tells you how much of the product will be obtained theoretically without the experiment. Now you do the experiment, then you will not get 3.3 grams. You will get always what? Less, because experimental errors are always there with us. We cannot get out of experimental. We cannot get 3.3 grams. That's almost impossible. Are you following me here? You will never reach theoretical yield 100% in the lab and in the industry itself too. There is always factors of errors. You can get 95, 96, 98. That's good, but 100% is almost impossible. That's really almost impossible. So, can I take this one out? Everybody has it? Now, the third step is they give you now, after the experiment is done, this value here after well, did I tell you that in Germany when I write it's something like, cannot be read very well, they call it chicken handwriting. Did you hear about chicken handwriting? Yes, I'm doing chicken handwriting now. I'm sorry about this because I'm writing on the wall. We'll see what we can do. I will take them. So after the experiment is done. After the experiment is done, we had gotten what? Less than 3.3 grams, correct? You cannot get 3.3 grams. It's impossible. If that's the case, I will be surprised. There is always an error there inside the lab or inside the factory. In the industry, the same thing. Always there is small tiny error there, 2%, 3%, 5%, always there. So then what is the yield? The yield is the actual one after the experiment is done, 1.7 divided by 3. That's the theoretical. This is the actual after the experiment done, after experiment, and this is the theoretical That's a real chicken handwriting, but I apologize. Theoretical, this is before the experiment. Before what? Experiment is done. And the whole thing here multiplied by 100%. And that's what they did. So this actual, this theoretical, gram with gram cancels out, and multiply by 100 get 52%. Everybody is looking? Any question? Any question? Okay, let's take one more. As I said, limiting reactants, I suspect will not come in ACS. It's just the time you have about, I don't know, 50 questions in 1 hour. That's still time is so, it's too short. So, can I take this one out? Everybody has it? Everybody has it? Okay, let's take this one out, and let's go for the another one. I liked it. This one is straightforward, but what type of reaction? We said the first one, single replacement. How about the second one? Oh, the answer is there, so I can't really hide those. So, what we call this compound here? This compound. See if you can. What this compound? What's the name of this compound? And where to find it and what we are using it? That has been each kitchen is there, I think. Unless you don't touch any cooking, you don't cook in your kitchen, then you don't have it. But if you cook, and in the lab, in every lab, it has to be there. What we call this? Don't Google it now. Don't Google it now. Everybody has it. Sodium what? No. Sodium hydro. Come on, guys, you are letting me down here. It sounds like Monday today. So do you have this? We'll have this here. Sounds like Monday today. This we call it carbonate. This one we call it hydrogen carbonate. What we call it? And then you can add the cation to it. Sodium, not hydro, sodium hydrogen carbonate, sodium, sometimes called bicarbonate. What's the commercial name of it? What's the commercial name of it? You have it in the kitchen, unless you don't cook at all in the kitchen. We have it in the lab for safety rules. We do have it in the lab. What is that? No? Baking soda, thank you. Baking soda. Don't tell me you don't have it in the kitchen. You have to have it, because if you cook any cake, any cookies, you need the dough to blow up a little bit, correct? You have to add a little bit of baking soda. The carbon dioxide will with the fermentation will blow up, makes the dough up. So we have it in the lab. Why? This is a weak base, correct? We need it in the lab. If anybody has accident with the acid, first we don't put that person inside just direct in the water, but we can put this one in the dish. But the small tiny stuff, we put a lot of baking soda on the acid place, and then rinse it with a lot of pepper. We have to have this baking soda to neutralize any acid accidents. Anytime you have an accident with the acids inside the lab, you can just put a lot of baking soda and then put the person under the douche, under the water, take a shower there for 15 minutes. So, but anyway, so this is what type of decomposition. If I heat one single arrow, I have one single baking soda or sodium hydrogen carbonate or bicarbonate. Baking soda is a commercial name. It's not a correct name for chemical name. It's sodium hydrogen carbonate, bicarbonate. That's the correct name chemically. So let's look at this. If have those here, one arrow means I have one compound will give me what? Two compounds. That's what? Decomposition. Just a review. Is that a quiz number 2, exam number 2? Was it? I think was it? Yeah, it was, correct? So type of reaction was in the lab as well, correct? Yeah, see? Yeah, so we did that. So let's look at this. I'm not doing 4. I'm doing something difficult with a lot of, yeah, this one here. This one, why difficult? Because it has a big molecules. So you have to do what? Molar mass, to calculate molar mass of those molecules, big ones. Not really big ones, but at least you'll have your time is consumed by calculating the molar mass, correct? So let's look at this. We have 2 steps here. Write the equation for the reaction of iron 3 phosphate. Iron 3 phosphate. Well, we know that's what type of reaction it is. Yeah, there is no type of reaction. Good, good. I like it. We can't cheat this time. What type of reaction is this? What type of reaction is this, guys? What's that? Some said double. Some, she said double. Who's saying double? Who's saying double?
No, that's single.
That's single?
Yeah, that's
Okay, let's
single.
open an auction here. Let's open an auction. For what price we want to sell this? Auction, double, single, what else? Guys, look at it. Just look at it. Iron takes what? Iron takes the sulfate here. Correct? And what does sodium is taking? It's taking the phosphate. Are they swapping their partners, the anion or the cation? Yes, they are swapping. The anion will take the cation for the second one. The cation for the second one will take the first one anion. So that's a double. So you are really, I feel like today is real Monday today. Double displacement or replacement, whatever you call it, your replacement or displacement. So that's double. She said double, but she was a little reluctant. So double, and then she comes in and out. Double, single, double. So you did not make your mind. No. I mean, you are happy with the answer, but this was a little bit of hesitance and reluctance there. Correct? Well, so that's double reaction. So now you can see, we have to calculate a lot of molar mass here. Can I take this one out? Just to show you double, so you know double. So now we have the chemical equation straightened up with the mole ratio 2 to 3 to 1 to 2. So 2 to 3 to 1 to 2. This understood, not written, but you have to write it there, right? So now number 2. If I perform this reaction with 25 grams iron phosphate. So this one here, I started with this molecule here. This here, iron sulfate, which is 25 grams. There is no decimal, but I like to put decimal always there to give just this suffix there. Correct? Okay, so 25 grams of this iron phosphate, that's my reactant there. This is my limiting. This is limiting. Why is limiting? This reactant is limiting because it said an excess of sodium sulfate. This one here, excess reactant, and this is limiting reactant. This one here. Okay. So we'll base our calculation on the limiting reactant, which is iron phosphate. We start whatever is given to us, 25 and decimal here. I will add decimal, guys, because that makes things much better with the suffix. As I said, sometimes whole numbers and you have decimal, the whole number will have nothing to say. The decimal will take over for suffix, correct? But if you put decimal there, that's 2 suffix. This is gram of phosphate. Next step is divide. Divide. You have to divide. And the last step is multiply. And this multiplication by the product, multiply product molar mass. So the step here, step 4. Step 4. This is step 1, the amount. Step 1. Always like this. Step 2, divide by molar mass of the reactant of limiting reactant. This step here is the mole ratio. Step number 3. Step 3, mole ratio. What's this mole ratio looking like? Will be looking like product, mole product to mole reactant. Correct? So we divide by the molar mass of the reactant. This is the reactant, the limiting reactant amount given to us. We divide it by its molar mass. You can verify that if you want to. So molar mass. Then we come to the mole ratio. I have the product is, we need the product to be what? We said, how many grams of iron sulfate? We need this one here. That's the product we are looking for. That's the product we are looking for. Desired product. That's a desired one. This is desired. Okay, guys? So I have 1 mole the product over reactant. So 1 mole here, 1 mole here. The reactant is how much? 2 mole of the reactants. And you can see the units is cancelling themselves out. Gram of the reactants per mole of reactants. Mole of the reactants here with the mole of the reactants. And then the molar mass of the products, which is very large, about 400 gram per mole. That's what I said. You have to spend some time to calculate those molar mass. Okay, molar, gram per mole. The mole cancels out. You get what? You get grams of your desired product, which is iron 3 sulfate, which came out to 33. I put the decimal on it here. 33 grams, 2 sig figs. Okay, guys, everybody's following? Everybody's following? Now, 4 steps. Step first is you put the amount of the limiting reactant started. Step 2, you divide by the molar mass of this limiting reactant. Step 3, you go to the mole ratio, product over the reactant from the chemical equation. Step 4, you multiply by the molar mass of the desired product you are looking for. Okay, guys? So, now, everybody has this? Everybody has this? Everybody? So, let's take this one out. And let's look at the... now, after this is before the experiment. Now, all this here, all this value here, this one here, sorry. This one here, before the experiment. Okay, now, after the experiment, you get this, the actual one. This one comes after the experiment is done. And you will never, ever, don't come to the point that you will get 33 grams. Never. That means your yield is 100%. That's not really true. So always your yield will be less. So because of the, just there are always errors. So 18.5 grams, that's the actual yield after the experiment. So then you will say, I have 18 after the experiment, correct? And I have calculated 33 point, that's before the experiment, that's theoretical, before the experiment, and that's my, we call it this actual. and this is theoretical. Before you start anything, so theoretical. This here, you multiply by 100%. And the answer is 56. With the decimal here, 56 decimal percentage. Okay, guys? I put this one here in iCollege already. This new, I did not see this one before. This is very good because it's nice steps, but the problem is they have some issues with the sig fix. So they have some issues with the sig fix. So, but anyway, but otherwise it's well done. It's a very good examples there, and worked out for you, so you can follow the steps there. So for the next quiz number 3, exam number 3, you might just print this one here in front of you and look. Okay, look at how they solve it, if there is one like this. And even in the Chem 101, if you find something like this, you know how to solve this one. Okay, guys, that will conclude chapter what? Chapter 5. I'll go for chapter 6. I'll stop recording.